Hmm. So, good evening, everyone. Welcome to the second live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Arshit Agrawal, a PMRF Research Scholar from the Department of Civil Engineering, IIT Bombay, and I will be taking a weekly live session for this course for the entire course duration. So first of all, for those who have joined the session for the first time, what is this course, these sessions all about? So these are weekly interactive sessions that are held every Tuesday from 6 p.m. to 8 p.m. And during the session, how would we interact? By answering to the questions that I will ask in the chat box, by posting your queries in the chat box, or by raising hand, unmuting, and asking your queries. Apart from the session, you can always use the discussion forum of the course where the questions will be addressed to the discussion forum itself or in the next live session. And attending these sessions regularly will help you to answer the graded assignments easily and will further develop understanding of complex topics holistically. So in today's session, we will first have a quick recap of week one session that we concluded last week, and then we'll move towards review of the week two learnings. So the week two recordings were oriented towards understanding the concrete behavior, where we first talked about material characterization, mainly in terms of cement. Then hardened state properties of concrete were discussed, which was all about the strength of concrete. Along with this, there was discussion on modulus of elasticity and long-term behavior like creep and shrinkages. And finally, we came to reinforcement material used in reinforced concrete and its role in design. So, along with the short theory recap of various parts of the last week content, in between, I will introduce you with several questions to challenge your understanding on the subject. So, in total, we will have around 25 questions that we will discuss today, and at the end, I will make myself available to solve any further queries related to assignment questions also. So whenever anyone has any doubt, they can just type in the chat box, and when in between when I will stop my presentation, I will see to your queries and we can discuss. Okay, so let's start. So last week we first saw what concrete is made of, basically in terms of a formula, which is a combination of a binding material, which is mainly cement, water, aggregates, and admixture. They all combine to make a initial slurry material, which over time gains strength and sets into a hard stone-like mass, which is known as concrete. Then we saw why we need reinforced concrete, because concrete is good in compression and weak in tension. So we add reinforcement. In reinforcements are embedded inside concrete to resist the tensile cracking, and this gives reinforced concrete system a compatible nature. Then we understood the design and the construction philosophy. Design follows a top to bottom approach where we start with slab, then beams, then columns, and then footings. And construction follows a bottom to top approach where we start from footing and end with slabs. And finally, we saw different design methods that are used for concrete design. So the design methods are of three types: working stress method, where only strength is modified with safety factor; in ultimate load method, the load acting on the structure is increased with safety factor; and in limit state method of design, both strength and load are factored to meet both serviceability and safety criteria. In common, all these three methods follow a common rule: load acting on the structure should be less than the resistance offered by the structure. Okay, so this was all about what we discussed in the week one. Now we will come to the week two discussion. So we know cement is a key ingredient in concrete because it acts as a binding material. So there are two main classifications of cement binding material in concrete. First is lime and second is cement. So lime has been used for building as a binding material for thousands of years, dating back to its ancient use in Egyptian, Greeks, and Roman times. Okay, in medieval India, lime was used in combination with surki to make mortars, which surki mortar, which is used to make ancient structures that you see of very old heritage structures that you see everywhere around. So just to simply understand how lime was used as a binding material, this is a lime cycle that we see here. So lime as a binding material is produced through this lime cycle, where limestone initially it is heated to produce quicklime, then it is mixed with water to form slake lime, and then it reacts with carbon dioxide from air to harden into limestone again. This cycle makes lime a durable, reusable, and a eco-friendly material. However, most of the modern construction that we see today is uses Portland cement. Okay, so let's first explore how this Portland cement came into existence. So it was in the early 19th century where one scientist named Louis Joseph Vickett, he prepared Portland cement by calcination of limestone and clay. Okay, and he laid the foundation for its development. And then in 1824, Joseph Espedin, he patented the hydraulic cement and called it as Portland cement. So this name Portland was chosen because of the its resemblance to a stone which was known as Portland stone, and it is found in area named as Dorset in United Kingdom. So from there it got its name as Portland cement. Okay. Now how this Portland cement is now produced in modern times, so it follows a five stage process. So first is the crushing of raw material, that we have lime, clay and limestone. Okay, so these material are crushed into small particles. Then the second step is grinding, proportioning and blending of these raw material, where these raw materials are grounded and blended into precise proportion to make a homogeneous mixture. Then this homogeneous mixture is heated using hot gases and preheat towers, which helps to reduce the energy consumption. And then they go into the kiln phase, where these preheated material are subjected to high temperature, where chemical reactions take place to form what is known as clinker. And finally, these clinkers are cooled and grounded with the gypsum to produce a fine powdery material which is known as cement. Okay, so these are the five process. First is the crushing of raw material, then grinding, proportioning, and blending of raw material, preheating of raw material, the kiln phase where the actual heating and the blending of raw material takes place, and finally cooling and final grinding with gypsum. Okay, why gypsum is added, that we'll see later on when we'll understand the hydration of cement. Now, after passing through the kiln phase, this limestone and clay, the raw materials that we are using, upon exposure to high temperature, they form different oxides of calcium, silica, and alumina after liberating CO2 and moisture. So, for a Portland cement, the composition of oxide is of the order that has been shown in this box. So, CO is around 60 to 67%, SiO2 is around 17 to 25%. Alumina oxide is around 3 to 8%, iron oxide is 0.5 to 6%, magnesium oxide 0.5 to 4%, alkalis are present in small amount 0.3 to 1.2%, and there is some amount of SO3 also 2 to 3.5%. So this is a standard composition that we get in Portland cement, oxide composition. Now these formed oxide, they blend into a solid solution to give different compound composition that is shown in this table. So the first composition is known as tricalcium silicate, which is also known as elite and represented by C3s, and it is in the proportion of 45 to 60% in normal ordinary Portland cement. Then we have dicalcium silicate represented by C2s, which is in the range of 15 to 30%. Tricalcium aluminate is represented by C3A, and it is in the range of 6 to 12%. Tetracalcium aluminiferrite is in the range of, it is represented by C4AF, and it is in the range of 6 to 8%. And gypsum is there, which is present of almost around 4%. Okay. Now, to understand why these compounds are formed from oxide to compound composition, how we came, we need to see how what is the structure of raw material and how they change over temperature. So, if you see here, I have one diagram. Okay, just a second. So initially, if you see, we have in this raw meal versus temperature diagram, if you see, initially we have limestone, clay and quartz and iron oxides which are present up till 600 degrees Celsius. They lose moisture and may even start, and the clay part, quartz part may also give some phase conversion from beta quartz to alpha quartz. Then beyond 600 degrees Celsius, calcium carbonate, it starts to decompose into CaO and liberate CO2 out. Okay. Then we have subsequently belite formation and calcium aluminate formation that starts. And then beyond 1200 degrees Celsius, we see belites are started converting into halide. While calcium aluminates, they starts to appear in the form of solid solution. So this is also one the difference between hydraulic lime and Portland cement. So in hydraulic lime, limestone is heated up till only 700 to 800 degrees Celsius. That's why the lime there is mainly composed of belite. However, in cement, due to high temperature or exposure, we have alite phase and belite phase both are present. Okay, so that is also one of the key difference between old cement and new cement in terms of manufacturing process. Okay, now just try to answer these two simple questions based on what you understand by lime as a binding material and the production of cement. And in the meantime, if you have any doubts, you can post based on our discussion till now. I will mute myself for a minute and freeze my screen to the question so that you can answer the questions. So can anyone tell me the answer for the first question? What will be the answer? Which of the following properties is the weakness of lime as binding material? Yes, this presentation will be shared later on by NPTEL team. Okay, yes, the correct answer is strength. So the weakness of lime as binding material is its strength. It has a lower compressive strength compared to modern binding materials like cement, which that and that's why it is not suitable for heavy structural load applications. Okay. Now, second question: what is the source of carbon dioxide emission in clinker production? So you saw this diagram. I will copy it here. So this is a diagram for clinker production. So basically, till this step, it is the clinker production, and then it is grounded and mixed with gypsum to produce cement. So what is the main source of CO2 emission in this process? Can anyone tell me the answer for the second question? Okay, let me tell you the correct answer for the second question will be both option B and option D. Okay, so first is the decomposition of limestone. So when limestone is decomposing, you know the reaction happening is CaCO3 is converting into CaO plus CO2. So this is one step where CO2 is liberated, and the second is the burning of fuel in kiln to produce that high temperature that we require for uh, decomposition of the blending of the raw meal. Okay, so here also CO2 is liberated due to burning of fuel. Okay, so in both these process, both these are the sources of CO2 emission in clinker production. Any doubts in these questions? Okay, let's move ahead. Now let's see how cement reacts with water. So there are two main phases that we saw in the compound composition. These are the silicate phases C3S and C2S, and we have aluminate phase C3. So these three are the main phases when we talk about cement because they are the one which are present in the maximum proportion. So first we'll see the hydration of silicates and then we'll see the hydration of aluminates. So in hydration of silicates, we have C3S and C2S, which upon hydration produces calcium silica hydrate gel and calcium hydroxide. So if you see here the reaction, so 100 grams of C3S, it consumes 24 grams of water to produce 75 grams of CSH and 49 grams of CH, while C2S 100 grams of C2S, it consumes 21 gram of water to produce 99 gram of CSH and 22 grams of CH. Okay, so this is the hydration of silicates. Okay, we'll see later on what is the difference between C3S and C2S and which proportion is required more, which proportion is required less. But right now you can just see minor differences: the amount of water it is consuming, the amount of CSH it is producing, the amount of CH it is producing. Okay, these are the key difference between both the hydration reactions. Now, in case of aluminates, C3A is very reactive due to its structure. Open, it has an open cubic structure, which makes C3A very reactive. So the reaction of C3A with water is very volatile, and this leads to immediate stiffening of cement paste, which is known as flesh setting. So if you see here, 100 grams of C3, it combines with 40 grams of water to produce 140 grams of calcium aluminohydrate, which causes flesh setting. Now, we don't want our cement to undergo such reaction, which makes it stiff as soon as we add water. So, to eliminate this problem of flesh setting and to make concrete pumpable or workable for practical application, gypsum is added at the end of clinker production. So when gypsum is present, it reacts with C3 and water to form ettringite, which is more stable and slow forming compound, and it eliminates this flesh setting problem. So if you see here, C3A, it reacts with gypsum in the presence of water to form C6A3H SH32, which is known as ettringite. Okay. Now as hydration continues, this available gypsum will get consumed over time. Okay, because we are adding it in very small proportion, only 4% is present in cement composition. So once this gypsum is depleted, and then still if there is excess C3 which is present in my cement, what will happen? This ettringite, it will begin to convert into monosulfate. So if you see, this is the ettringite which was formed due to reaction of cement and gypsum C3A and gypsum in the presence of water. Okay, ettringite was formed, and if there is excess of C3A still present in the system and there is water present in the system, so this ettringite will convert into this compound C4AS ASH12, which is known as monosulfate. And this conversion of ettringite to monosulfate is involves. Does anyone have any question? diplomatic answer. Okay. So this conversion involves a reduction in value volume, which can lead to some minor shrinkage problems also initially during hydration. Now, in hardened state, when sulfate intrudes the concrete, what happens? This monosulfate will again try to convert back to ettringite, and this is something which is known as reformation of ettringite, and which can cause significant volume expansion and damage in concrete. So later on, when we will talk about durability of concrete and sulfate attack in concrete, this is the reaction that is occurring when we talk about external sulfate attack. Okay, so for now you can just remember what is the role of gypsum and what will happen if there is excess C3 present in the system, and what is the role of sulfate in these reactions. Okay, we'll have a detailed discussion later on in durability class. Now let's talk about kinetics. Like, this was just how cement is reacting with water, but what rate the reaction occurs. Okay, so kinetics means the rate at which hydration is occurring. So in the first figure, we can see that in the initial few hours, we can see this C3A and C4AF, it starts to react. Okay, and this period is known as dormant period, the initial period. Then in the acceleration period, we see C3S also starts to react, and finally in the post acceleration period, C2S also starts to react. So you can see here, this is the progress of hydration and this is hydration time. So C2S shows growth in hydration in the post acceleration period, while in acceleration period you can see a major rise in the hydration of C3s. Okay, while in the second figure you can see the amount of hydration product that is formed over time. So you can see initially in the dormant period, there is a very small quantity of hydration product which is formed, and which is mainly a small amount of CSH and alumino ettringite, okay, which is mainly formed due to the reaction between C3A and gypsum. Okay, in the setting period where we see a little stiffening in concrete which starts to happen, we see there is more amount of CSH and ettringite formation taking place. And then in the hardening period, we see this ettringite starts to convert into monosulfate if the gypsum is completely consumed and still there is C3A present in the system, while there is a increment in the growth of CSH, and CH also starts to form, that we saw in the hydration of silicates. Okay, now this hydration reaction that we talked here right now in different equations, these are exothermic reactions. Okay, and these different compounds C3S, C2S, and C3A, they liberate different amount of heat upon hydration. So if you see this table at the top, it lists the heat of hydration represented in joule per unit gram of compound undergoing hydration. So you see C3A, it undergoes it releases the maximum heat during hydration, followed by C3A, it is C3S, then C4AF, and then C2S. Okay, so this is the rate at which heat is released for per unit consumption of these compound when they react with water. Okay, so and this is known as the heat of hydration. And if we know the chemical composition of our cement and we know these value, we can compute the total heat of hydration of a cement system also. And based changing these composition, we can alter the heat of hydration based on the requirement or based on the condition in which the cement is used. Okay. Now just try to answer these questions based on hydration and reactivity of cement that we just discussed. One of these questions where you see this image. So this is just a part of additional learning. Okay. So here you see in this image, this is a SCM image of 7-day hardened paste cement paste system, and it has different hydrate formation phases which are present. So I will just, if you don't know about these different how different hydration product looks, so I will just tell you here, how where are they located and how they are appearing in this image. But just give it a try. This question and other questions also. In the meantime, if you have any doubts in the discussion that we had till now on basics of cement and cement hydration, you can ask in the chat box. Yeah, water. You're not getting disturbed. Teaching private college students, that's very difficult. They don't know anything. For them, it is too much. They are just asking in chat box where you will share the PPT, where we will get the video. No, they ask last session. I don't know. I have never seen their exam. No, some assignments are there. Assignments are very easy. That's why I don't discuss assignments. In this course right now, there are not those many students. Hardly maximum 10 students are joining live session. Usually I had 50, 60 students last time. So it will always be about discussion more than no, this is a reinforced concrete design, advanced reinforced concrete design. So it is not based on IS code, but it is mostly based on the outcomes of strength testing, tensile testing, and how it can be used to design concrete. So right now, the initial 3 weeks is all about basics: concrete, strength, creep, shrinkage. It is a 4 month course, 3 month. Yeah, it is free. They can enroll for free, but for certificate they need to give exam, and for that they need to pay fee. Okay, let's see the solution now. Okay, so from durability point of view, which clinker phase is more important? So the right answer is C2S. So if you see this hydration reactions, so C3S, it produces lower amount of CSH and more amount of CH upon hydration, while C2S, it is producing more amount of CSH and lower amount of CH. Okay, so this CSH is something which is the main strength contributing phase in cement hydration, and more is its amount, more durable my concrete will be. And CH is something that is not desirable to us. It is a waste product. It just gives the pH to the concrete. However, it is the weak link also in terms of durability issues to concrete. Okay, later on we'll see how it is the source where carbonation of concrete is happening, and how it is the source for other durability problems also. So that's why having more C2S in the cement composition rather than C3S is better for a cement. Okay.
There's a please present in display mode. It is not visible very good.
Okay, okay.
It is
Is it visible now? Can you reply?
it is it is not in presentation mode.
Now it is in presentation mode.
Mm,
See, is it visible now?
Please any other confirm for me. It is only a small display showing.
Can anyone
I
else
think that is
confirm? Are they able to see the slides properly or not?
okay, sir. It's visible only.
Okay, okay. It might be your issue because others can see the slide properly. Just check,
Okay, okay, I can
try to
understand, sir.
reconnect once. There might be some network issue on your side which will make presentation not clear. So you can just reconnect. Okay, else this presentations will be shared to you, so you should not worry about that. Okay, just I hope you understood what was the reason. C2S is producing more CSH and less amount of CH. CSH is desirable to us, CH is not desirable to us. Okay, so from durability point of view, having more C2S in the cement composition is beneficial to us. Okay, now second question, identifying the hydration products from the image. Okay, so if you see, this is what I told, 7-day hydration SCM image, okay, of a cement paste system. So you see here at the bottom left side, this this is the CSH, okay, a cement particle coated with CSH structures. Okay, these needles that you see, these are of ettringite. These are ettringite needles. Here at the top, this plate structure corresponds to monosulfates. And somewhere in the middle, if you see large hexagonal crystals, okay, so where you can see at the right top, okay, here these large hexagonal crystals that you see, these are calcium hydroxide. Okay, so I won't go deep into the structure of cement hydration because this is beyond the limit of this course, but this was just an explanation how from a SCM image generally we quantify where all different products are formed. So CH has a hexagonal crystalline structure, CH has this gel-like structure, then needle-like structure is of ettringite, plate-like geometry is of monosulfate. So in this way, we can distinguish different hydration products that are formed in cement hydration. Okay. Someone is unmuting the mic again and again, which will disturb others also. Just if you have any doubt and you're not able to speak, or there's some connection issue, just type in the chat box because I'm regularly checking the chat box. I will respond as soon as possible. Okay. Question number 5. What is the order of reactivity of clinker phases? So we just saw in a while ago when we talked about this react hydration, degree of hydration. So the correct order of reactivity is C3A. It reacts quickly. Then we have C3S. Then we have C4AF and then C2S. C2S is slowest in terms of reaction. Okay, so C3A will be first, then it will be C3S, then C4AF, and then C2S. Okay. Estimate the total heat liberated. So this is very simple question. Okay, here we have the table. Okay, I will just paste the table here. Okay, here I can see the values. So what we need to do, we just need to multiply the composition of cement with the amount of heat liberated. So suppose I have 1 gram of cement, okay, in which I have 50% C3S, 30% C2S, 12% C3, and 8% C4AF. So per gram, how much heat is liberated, we know. So for C3S, it will be zero point 0.5 times 502, then plus zero point 0.3 times C2S liberates 260 joule heat per gram, then it will be 0.12 times 876 plus 0.08 times 419. So like this we can calculate the total heat liberated by a chemical if we know the chemical composition of cement. Okay, so this calculation you can do, you will get the answer. Okay, I will just do calculation once to just give you the value what is the answer.
So 466.56 joules.
Yeah, I'm just checking. 502 into zero point 0.5 plus 260 into zero point 0.3 plus. Yeah, 466.56 joule. Okay, so this is the total amount of heat liberated. So this value, importance of this value will get later on, just in the next discussion when we talk about different types of cement, and how these different types of cement, why they are present in the industry, where we want a cement which should release low heat, we want where we want system which can have high heat of hydration. These things comes when we talk about different application areas, and where which cement will be most suitable, so there such values comes into importance. Okay, any doubts in these four questions?
Also,
Okay, let's move ahead then. Now, there can be different types of cement. Okay, and how these cement differ from each other. So they differ mainly in terms of their composition and physical properties. Okay, and the composition and physical property, they can have a favorable change in the reactivity of cement also. Now, so by varying the composition, we can vary the reaction kinetics of cement and suitability of cement to a certain special requirement. Okay. Why such composition, like why we need different types of cement, so that we can make a suitable binding material for based on a project constraint, which can be due to location, application, and exposure related. Okay, so this variation, when we talk about composition, they can be dependent upon the proportioning of the raw meal, or in the way the cement is produced, or later on proportioned. Okay, now the different proportions of cement, there are different classifications of cement, out of which I'm just listing here three types. So one is the ASTM classification of cement, where we have standard modified classification of cement, which are named as ASTM type 1, type 2, type 3, type 4, and type 5. We have special purpose cement like high alumina cement, super sulfated cement, white cement, and expansive cement. And there are blended cement where OPC, the ordinary Portland cement, is substituted with mineral admixtures like fly ash, ground granulated blast furnace slag, and silica fume. All these cements are produced so that we can have a optimum proportioning of binding material based for our application and exposure. Okay. Now, for all these classification of cement, the base is the composition of cement. So, by varying the chemical composition, we are varying the reaction kinetics of the cement. And this variation in chemical composition is, as we said, it is dependent upon the proportioning of raw meal and its quality, which makes the variation in the oxide composition. So if you see different what is the role of different compounds that are present in cement in hydration. So we know elite, it is the main strength providing phase, early strength providing phase, because we saw hydration of C3s, it produces CSH and CH. And CSH is the main strength providing phase of cement hydration. Okay, and this reacts early also. So that's why we have said main early strength providing phase of cement. Belite, it is slower in reaction. However, it also gives late strength gain in cement hydration. Aluminates, it reacts fast and cause flash setting. Ferrite, it also reacts fast, but it is self-retardant, so that's why we don't talk about ferrite hydration much. There are alkali sulfates which can accelerate the early strength growth. There are calcium sulfates, which is gypsum, which act as a set retarder. So we saw aluminates, if they cause flash setting and we add gypsum, it converts aluminates into ettringite, which delays the setting. Then there's magnesia, which can cause soundness problem, and freelime, which can also cause soundness problem. So if we are changing the proportioning of these compound phases in my cement, in a cement, we can change the way it is hydrating. Early hydration, late hydration, the amount of heat liberated, more or less, those variations can be made. And the basis of the cement classification is the phase proportioning. So let's see one of these classification, that is ASTM based classification. So ASTM is basically American Society of Testing and Material, which has classified cement into five types. Okay, under this coded provision, ASTM-C 150 standard specification of Portland cement. So these type they differ in terms of chemical composition, physical property, and its intended application. So in this table, we can see some minor and major changes in the compound composition of each of the five types of ASTM cement. So this is type 1, 2, 3, 4, and 5. In type 1 cement, it is just a conventional OPC. Okay, ordinary Portland cement. So we can see from the proportion, C3S is around 50%, C2S 25%, C3A 12%, C4AF 8%, and calcium sulfate is 2.9%. And it is a conventional OPC system. In type 2 cement, compared to type 1 cement, we see major changes in the quantity of C3A, which is reduced from 12% to 6%. So if there is less C3A, the thread for sulfate attack will be reduced. So earlier, if you remember in our discussion, we saw C3A reacts with gypsum to form ettringite. If there is more amount of C3 in the system, ettringite converts into monosulfate, and externally when sulfates come into concrete, monosulfates can again convert back to ettringite, which can cause cracking in concrete. So if initially C3 proportioning is less, that ettringite to monosulfate conversion will be low. So delayed ettringite formation chances will also be lower. So sulfate attack chances will be lower. Okay, so that's why this type of cement is called modified Portland cement. Then in type 3 cement, we have compared to type 1, we have higher proportions of C3A and a lower proportion of C2S. What is the cause? What does this cause? So C3S has a higher rate of reaction and C2S has a slower rate of reaction. So more C3A will make cement rapid hardening, and thus this type of cement is known as rapid hardening Portland cement because it has more amount of C3S in the system. Then we have type 4 cement, which compared to type 1, there is a higher proportion of C2S this time and a lower proportion of C3S. So this will be like just opposite to type 3, it will be a slow strength gain cement. Okay, since C3S is smaller in quantity and C3A also is smaller in quantity, so the heat liberated by this cement also will be lower. So that's why it is known as low heat Portland cement. Okay, we saw in this table, if you remember, amount of heat of hydration in joule per unit gram. So C3S and C3A has the maximum heat of hydration and C2S has a lower heat of hydration. So since in this type we are reducing C3S and C3A proportion both, so this is a low heat Portland cement. Okay, and then we have type 5, which compared to type 1, if you see C3S and C2S proportion is more, C3S is comparable with, it has a very low C3A content. Okay, so this type of cement is known as sulfate resisting cement. Okay, because of its very small sulfate C3A content. Okay, so like this, based just by varying the oxide, the compound composition of a cement, ASTM has generated five conventional types of cement. Like ASTM, our Indian Bureau of Indian Standard also classifies cement into different major categories, and each of this category has a standard provision that has been set for practical utilization. Like we have ordinary Portland cement of grade 33, 43, 53, for which we have IS 269 code. There's Portland low heat cement for which we have IS 1012600 code. There's rapid hardening Portland cement. There's Portland pozzolana cement where with OPC we have uh, 15 to 35% of fly ash that is added as a replacement of OPC. That is known as Portland pozzolana cement. Then there's Portland slag cement. So here OPC is replaced by ground granulated glass, the blast furnace slag. There's sulfate resisting cement, which will have a very small proportion of C3, like we saw in ASTM classification. And then there is a type which is known as composite cement. Okay. Now, try to answer these two questions. So these two questions are based on the ASTM classification of cement. Okay, and just try to see the first question here. I have given a composition, and I need you to find which is the type of this cement. What is the ASTM type? And the second question, I have given you different application areas. And for this application area and using this table, you need to choose which type of cement will be most suitable for the application. Okay, just give it a try. I need to increase the speed. 1 hour is left over, and I am just at slide number 20. So for question 7, yes, the correct answer is type 4. So if you see from the composition, there is very small proportion of C3A in the composition. Okay, so this resembles with the type 4 cement, and the other proportions are also near the same proportion that we fix for type 4. Okay, so this is a low heat Portland cement. Okay, for this table, you need to refer to this. For this question, you need to refer to this table, so you will get a idea how to which to which gray to which type this composition can belong. Okay, but for answer, you just need to check these three values. From these three values, you can identify the type. Now, try to answer question number 8.
మొలకల
మొలకలు వచ్చినాయంటే ఏమైంది నానేసింది నిన్నేగా ఇప్పుడు ఉడకబెడితే
So the correct answer for question number 8 will be A. So some of you has answered correctly. So cold weather concreting with rapid strength gain. For this we require, if we want a rapid strength gain, we require a rapid hardening Portland cement. Okay. Dam construction for minimizing heat generation. For this we need a low heat Portland cement type 4. General construction in non-aggressive environments, that will for that conventional OPC will be suitable. And exposure to high sulfate concentration, then we need a cement which has very low quantity of C3A, so that will be sulfate resisting cement. Okay, so the correct answer will be A. Okay, so this is how, based on the application area, we can choose different suitable cement. Okay. Now let's come to the hardened properties of concrete and what are their contribution in the design process. So when we talk about concrete, we are mainly concerned with the strength of the concrete. So strength of concrete refers to the ability of concrete to resist force without breaking or deformation. And when we talk about concrete, it exhibits four different types of strength depending upon the direction and the type of force that is applied on it. This compressive strength, which is resistance to axial compression. This tensile strength, which is resistance to axial tension. This flexure strength, which is resistance to bending force. And this bond strength, which is the addition between the reinforcement and concrete. So strength basically determines the load carrying capacity of a concrete structure. If you have a higher compressive strength, we ensure that our concrete has higher longevity and safety. And tensile and flexure strength are critical in applications like beams, slabs, and bridges, where there can be tensile stresses which can generate, while bond strength affects the interface between the concrete and the reinforcement, and it ensures that my reinforced concrete is acting as a composite. Okay, so today we'll discuss about compressive strength and then we'll move into this tensile and the flexure strength. So on this slide, you can see two stress versus strain relationships for compressive strength, which are derived from compressive strength testing. So in the first one, you can see how different grades of concrete perform under compression. So this is how the grade of concrete is increasing. Okay, this is for the lowest grade. Maybe it will be M15, M20, M25, like this we are going up to a higher grade M60 or M55, M60. Okay, like this the grade of concrete is increasing. So if we see as the grade of concrete increases, the peak load, okay, this is more than M60, yeah, this is more than M80. Okay, so as we see, as the grade of concrete increases, the peak load, which corresponds to the compressive strength, also increases. However, along with this, the strain at which this peak is achieved, the strain, or we can say the deflection incurred by the concrete to reach the peak load, it also increases. So if you see from this dotted line, the strain corresponding to peak is also increasing. However, if you see the post peak behavior, you can see there is a sudden drop in strength, okay, happening, and this drop in strength is faster in higher grade concrete compared to lower grade concrete. Thus lower grade concrete, they deform more till complete failure, and thus they are more ductile, while higher grade concrete, they show brittle failure. Okay, so this is the effect of concrete grade on the stress versus strain profile when concrete is subjected to compression. In the second figure, we can see this the same stress versus strain profile, but for in different ingredients of concrete and concrete itself. Okay, so we see aggregates, they are stronger in compression. Okay, they have a very steep slope. Okay, so you can see they have a higher strength and they achieve the strength as a at a lower strain value, while cement paste, just a second. Okay, while cement paste, they are weak in compression, but they have a larger strain, and say concrete in between comes in between these two types. Okay, lies somewhere in the middle of these two. So when we talk about failure, that's why we say the failure occurs due to crack propagating to the cement paste and not through aggregate, because aggregates are stronger ingredient when we talk about a concrete as a composite. However, when we go to high strength concrete, this we increase the paste strength. Okay, so this paste strength you see here, it will be increasing like this. Okay, and your cement concrete as a composite will be coming like this. Okay, so the cement paste curve, it is getting closer to the aggregate curve, and now crack may even pass through aggregate also. So this tells us how concrete ingredients can control the strength of concrete. Now, in compression, when we talk about cracking of concrete and failure, it is governed by the pores and the presence of initial cracks inside the concrete, because they are the one which gives the weak link for the crack growth. So there are three components in the concrete system. We have the aggregate skeleton, we have the cement paste, and we have the interfacial transition zone. So this interfacial transition zone is the interface between aggregate and cement paste. Okay, and these zones have higher, more porosity and cracks than other two parts. Okay, so that's why when we talk about failure, the cracking in concrete, it passes through this interfacial transition zone in concrete, that we can see in this image also, the fracture plane. Okay, how it is propagating inside concrete. So this figure just summarizes this entire compression failure of concrete. So initially we can see in this first image the cracks are initiating in the ITZ near different aggregate and cement paste regions. So this is aggregate that you see in dark color, and in between this light gray color represents the cement paste. So you can see several red lines which are marked, which shows the cracks initiating at the ITZ. Now, as the loading increases, these cracks they connect and they propagate to form bigger cracks. So you can see here the cracks are connecting between two ITZs. And finally, when they connect to give rise to a failure plane, this results in a compression failure, which you can see in the last image, how these cracks are completely connecting and propagating throughout the cross section of concrete. Now, if we see this in terms of strain profile, the longitudinal strain that is represented by this red line, it shows a steady increase in the first two stages. Okay, crack growth and crack propagation. Okay, however, it then shows an exponential growth in the last phase. Okay, when these cracks are propagating and finally connecting to form a failure plane. The lateral strain, so this is the longitudinal strain epsilon 1, and this is the lateral strain. Okay, so lateral strain, you see, it shows a very small uh, increase in the initial two phases, but it shows a drastic increase in the final phase when the cracks are already getting connected. However, if you see the volumetric strain, it is positive for the first two phases till here. And when the crack propagation becomes unstable, when these cracks have already connected and now they are able to form a failure plane, the tensile stresses they starts to dominate, and we see a shift in the volumetric strain profile from positive to negative until the failure occurs. And this justifies the failure pattern also that we observe in concrete, where when we test concrete in compression, we see that failure occurs from this side due to bulging of concrete from here. That is due to the tensile stresses which are generating at when the crack completely connects. Okay. Now, it is not just the internal factors. So, here in this graph, we talked about grade of concrete and how it is dictating the strength of concrete, the proportioning of aggregate, cement, paste, everything. So, it is not just these internal factors which can affect the strength of concrete, but often in case of laboratory measurements, in laboratory, when we design a concrete and we test the concrete, the testing setup and the condition can also greatly influence the strength of concrete. And that's why there we have standard provisions which are made to conduct compressive strength testing. So if you see, these are different clauses which are present as IS 516 guideline for compressive strength testing of concrete. Okay, and different clauses mentioned here are mentioned here specifies different specific testing condition. So you can see as an example, a clause 2.8, so are they saying test segment should be cubical in size of 15 centimeter side, and there should be no aggregate surface maximum aggregate share size should not exceed 20 and if it is not exceeding 20 then 10 side cubes can also be used. If cylindrical samples are used, they shall have a length equal to twice of diameter, and they shall have a 15 cross section, 15 in diameter and 30 in height. So these are different specifications this clause is mentioning for uh, size of concrete. Then in clause 2.11, it is mentioned ends of the cylindrical sample that are not plane within point 0.5 shall be capped. So capping is done if the surface area is not, if the surface is not plane. Clause 5.3 and 5.5 says that The strength testing should be done at 7 days and 28 days. It should be stored in water immediately after removal from mold and stored in wet condition until the testing is done. Loading shall be applied at a very specific rate of 40 kg per centimeter square per minute. And if we are doing a cylindrical sample testing and we are doing a cube sample testing, the strength will be different. So the equivalent cube strength of concrete shall be determined by multiplying the corrected cylinder strength by a factor of 5 by 4, that is 1.25. Okay, so if we get the cylindrical strength, multiplying it by 1.25 will give us the equivalent cube strength, okay, in terms of what we want to report. Okay, so these are different testing criterias also which can affect the strength of concrete. Now we will see one such effect. What is that? Is the shape effect. Why we are talking about cube and cylinder, and why there is a conversion factor. So this conversion factor is due to a reason effect which is known as end platen effect. So generally, when we test concrete in for compression in lab, we have two shapes. Either we are testing for cylinder or we are testing for cube. So when we have a cube which is getting compressed between two plates for compressive load, so you can see here these blue plates are steel plates and this is the cube in between. So the surface of the cube which is in contact with the plates, it will be tried to be pulled inside. However, the friction between the plate and the cube will tend to resist this force. Okay, so there will be opposite movement. Okay, the force that is acting, the compression force, will try to push the cube outside. However, the frictional force between the plate and the cube will try to move the force cube inside. Okay, so this effect, this end platen, this frictional effect is something which is known as end platen effect, and generally it resists up till a depth of 0.866 times the diameter of the sample. Now for cube, my diameter is 0.5d. Okay, and this 0.86 is more than 0.5d. So you see this end platen effect, it can go up till the entire length of the cube. Okay, so however, for cylinder, when we talk about cylinder having diameter d and height 2 times the diameter, this end platen defect doesn't correspond to the complete length. So you see here in this cube, it is corresponding to the complete length of the cube, depth of the cube. However, for cylinder, there is a weak zone in between where there is no end platen effect and there is just this tensile effect that is generated by the compression load. So that's why in cylinder we observe a lower strength due to the presence of this weak plane which is there in between, where there is no resistance offered by the platen effect. And in cube there is the entire cross section which is under the end platen effect, and that's why it has a slightly higher strength compared to cylinder. Okay, and this is how you observe the failure when you test cube for concrete. Okay, this is the weak plane that is generated. Okay, so here there is more resisting force slowly decreases in the middle, and this is why, that's why here there is the bulging or the concrete rupture that happens. Okay, and in cylinder we have a complete weak zone in between there where this resisting force won't go. Now just try to answer these three questions based on the basic discussion of strength of concrete. In the meantime, if anyone has any doubt in this discussion that we had right now about end plate and effect and the effect of size, dimension, curing type, and all. And this failure of concrete cracking, ITZ, they can ask. Okay, I got answer for all three. Okay, let's see these questions so that we can move ahead. As I see in the chat box for ninth, yes, the correct answer is D. So the presence of naturally occurring cracks in concrete can be due to all these three regions: shrinkage, thermal expansion difference, and ITZ weakness. So that's what we have discussed in the content. So this is an easy question. Okay, all of the above will be the answer. Which type of pores in concrete contributes most significantly to the reduction in strength? So it is the capillary pores. So capillary pores are the basically the macro pores that are present in concrete. So pore distribution in concrete is of different sizes, in which macro pores are generally corresponding to the capillary pores. And capillary pores are formed due to excess of water that we add during mixing. Okay, and if there is more pores inside the concrete, lower will be the strength of the concrete or the load bearing capacity of concrete. Okay, ITZ voids and gel pores are minor pores, they are not as big as capillary pores. Okay, and air entry in voids are sometimes beneficial, sometimes harmful, but mainly the capillary pores are the one which significantly reduce the strength. In high strength concrete, fibers are added for strength enhancement. What this fiber reinforcement, how does fiber reinforcement do? So they bridges the micro crack and prevent their propagation. So we saw when we talked about how the failure is happening. So initially cracking starts at ITZ, and then these micro cracks are connecting with each other. So what happens if these fibers present in my concrete matrix? What fibers will do? It will bridge this micro cracks from growing, and it will delay their propagation. And if their propagation is delayed, the failure planes won't form easily, and thus it will improve the strength of concrete. Okay, and that's why when we talk about high strength concrete, generally above M80 or M100, fibers are generally commonly used in a mixture proportioning. Now answer these two more questions. So these questions are basically related to the external conditions which can affect the strength of concrete that we saw based on IS 516. So very simple questions, just try to answer. Okay, yes, for 12, the correct answer is A. Okay, so in this question, two cubes were given of different size. First was 150 cross 150 mm, and second is 300 cross 300 mm. And we observed that smaller cube has a higher strength compared to larger cube. So the reason for this is the size of the cube. So more is the size of the cube, higher are the chances of having internal defects and micro cracks, which can lead to early failure. So for this, I had this slide also, which I wanted to show. Okay, so larger specimen shows lower strength than smaller specimen because higher probability of defects that are present in the system. And in IS 516, you can see the correction factors also, they are available for different size. Okay, so this is for cube. Okay, for 70 mm, 100 to 150 mm, 200 mm, 300 mm, they have given different relative strength factor. So relative to 100 mm cube, as we increase the size, the strength decreases. As we lower the size, the strength increases. And for cylinder also, based on H by D ratio, ASTM, Bureau of Indus Standard, and IS code, they provide different correction factors, okay, for strength. Okay, so if my HYD ratio is lower than 2, then strength is overestimated due to the lateral confinement. So we will see that weak failure plane that is present in between, it will reduce. So we get an overestimated strength. However, if the HYD ratio is more than 2, then buckling failure can occur, which will reduce the strength. And that is reflected in the correction factors that we see here. Now try to answer question number 13. So here three specimens are given which are cured in different conditions, and you need to tell me what will be the order of compressive strength. Okay, so for question number 13, the correct answer will be, so yes, the correct answer will be B. Okay, so first sample, it is moisture in 95% relative humidity for 28 days. So this will ensure that there is no evaporation loss from water, and proper curing is achieved in concrete. Sample B, it is cured in open air exposed to when in sunlight. So there can be, there is inadequate curing that is happening. And third, it is cured in water but oven dried before testing. So that can also hamper the strength. Okay, so yes, the correct answer is B. Now, how compressive strength contributes to design? So we know concrete design is primarily based on strength requirement, or we can say it is strength oriented. So if you see how we represent concrete, we represent it based on strength as M20, M40 or M60. So here M represents the mixture and 20 represents the characteristic compressive strength at 28 days. Okay. So it is represented in terms of grade, and this is how grade is represented. And what is characteristic compressive strength? So we have seen in the last session, it is defined as the strength of material below which more than 5% results will fall. So it is mean strength minus 1.6 times the standard deviation. Okay. Now, based on this IS 456, they have a table which classifies concrete into different types. So there is high strength concrete, which is above M60, M55 actually. Standard strength concrete is M25 to M55, and normal strength concrete is M10 to M20. So based on the grade of concrete, different classification of concrete can be generated for design purpose. Now, during design, we don't directly use this characteristic compressor strength. So we know the FCK value. Suppose we are designing M20 grade concrete. Okay, so we know characteristic compressive strength is 20 MPa at 28 days. However, we for design we don't use directly use this FCK value. Rather, we use a factored FCK. So this stress strain diagram, if you see at the top, I will just zoom it. So this stress strain diagram represents the idealized stress strain curve for concrete under compression. Okay, so which is commonly used for limit state design. Okay, so let's see what are these reduction factor or factored FCK, how we obtain. So first of all, FCK represents the cube compressive strength here. Okay, which is determined from 150 cube. Okay, now concrete in structural design does not reach full cube strength in practice. Okay, especially when we are talking about cylindrical samples. Okay, therefore we need a conversion factor of 0.67 to account for the difference in the cube strength and the cylindrical strength. So this initial conversion factor is for the shape of concrete. Okay, now the second conversion factor, that where we have this factor gamma m, it is the partial factor of safety of material, which is typically 1.5 for concrete as per IS 456. So these reduction factor, they ensure that the structural safety is applicable to worst case condition, accounting for the variability in material property, inaccuracy in construction, the shape of the construction, and long term effect. So this is how this FCK is factored into 0.67 FCK upon gamma m, and this gamma m value is generally 0.5, 1.5, and so this 0.67 upon 1.5 will give us 0.45 FCK. Okay, so if you see an idealized stress strain block for reinforced concrete that I have shown at the back. Okay, so you see the extreme compression fiber we have taken, it is taken as 0.45 FCK, and this correspond to a maximum strain of 0.0035. So this is the role of compressive strength in the design. Okay, and this, you if you have done reinforced concrete design using IS 456, so you know this stress strain block using this area under compression and area under tension, it is used to calculate the amount of steel reinforcement required to be provided if we know the bending moment acting on a concrete, reinforced concrete. Okay, so this is the basis how we get this 0.45 FCK. Now IRC 112 code also provides some table for compression design. Okay, so these IRC code, they are mainly used for bridge construction engineering. So if you see here in first table, it is the main group of concrete and its strength grade. So there are different grades of concrete that they have specified for ordinary concrete, standard concrete, and high performance concrete. Okay, these are the stress strain profiles. So this profile we have already seen, a parabolic profile, and this is the uh, simplified stress strain profile. And for this they have a table 6.5, there they have listed different properties for different grade of concrete. So what is FCK, what is mean strength, Okay, what is the 0.5% probability strength, 0.95% probability strength, modulus of elasticity, strain, ultimate strain, and peak strain value, and all the values they have listed in this table for the different grades of concrete. Now after compression we have modulus of elasticity. So modulus of elasticity, basically if you see here in compression testing, it in the elastic zone, it is the ratio of the applied stress to the corresponding strain. Okay, and it defines the ability of a material to resist to withstand deformation when the stress is applied on the material. So if concrete is stiff, it will deform less under a certain applied stress, and thus it will have a higher modulus of elasticity. So if we talk about M60 grade concrete and a M25 grade concrete, M60 grade concrete will have a higher modulus of elasticity since it is stiffer compared to M25 grade concrete, and thus it will deform less when a certain stress is applied on the concrete. Okay. Now there can be multiple ways in which MOE value of concrete can be estimated. So if you see, this is generally a stress versus strain profile that we obtain under compression for concrete. So this is not a very linear profile. Okay. So there can be multiple ways in which MOE of concrete can be estimated. Okay, because of this non-linearity. MO is a ratio of stress to strain, and that can change with the slope of line also. So that's why there are multiple ways to estimate MOE value. First is the initial tangent modulus, where the slope of stress versus strain curve at initial loading here. Okay, you'd see the slope we are drawn at the initial point. So from this we determine the MOE. So this is known as initial tangent modulus. Then there is instantaneous tangent modulus, where slope of stress versus strain curve can be taken at any point. So suppose at any intermediate point, suppose at this point I want to estimate the MOE, I will just draw a tangent at that point and estimate the slope. Okay, so that is instantaneous tangent modulus. Secant modulus is where the first point and the last point is connected and MOE is determined. So this is my peak, this is my first point, and using this I will determine the MOE value. Okay, so that is secant modulus, and quad modulus is similar to secant modulus, but here we choose intermediate points. Suppose this point and this point, to intermediate point I will choose, and using these 2 points I will determine the slope of the line. So that is known as quad modulus. Okay, so these are different ways in which MOE value of a concrete can be determined. Now I have two questions for MOE, like which I guess is beyond, which was beyond the content of this course, but it is a very interesting part that I want you to understand and answer. So just think about these two questions. Why concrete shows a non-linear elastic behavior? So we saw this profile. This is non-linear and inelastic. Okay, so why inelastic? Because upon unloading, you see there is no complete recovery in strain. Okay, that's when inelastic and non-linear, because it is not increasing linearly. So why is such behavior present in concrete? And second, how we calculate modulus of elasticity in lab, like in laboratory testing, how this is determined. So these two are a little theoretical question. If anyone knows the answer, just try to answer. Else I will tell you the basis behind it. यार बहुत सारा बच्चा है, जल्दी करो. So let me just discuss the solution for these two, because I don't expect anyone to like answer to these two questions, and we have a lot of theory yet to cover for this session. Okay. So for first question, why concrete is showing non-linear elastic behavior? So I have explained you the meaning of both the terms. Non-linear because it is not increasing linearly, and elastic because it is not completely recovering the strain after removal of load. So when we talk about different stress level in this curve, okay, so suppose we categorize this curve into three stress level up till 30%, okay, stress, then up till just near ultimate, and then ultimate. Okay, so when the load is applied up till 30% of this peak load, what will happen? Microcracks starts to form in the itz that we have already discussed when we talk about failure in concrete, how failure occurs in concrete. So this curve already deflects from the straight line because which indicates non-linearity is reached. Why? Because of the micro cracking that is happening in the concrete. And here if we will remove the load, we will see only a small permanent strain will remain. Most of the deflection will be recovered because there is still micro cracks in the ITZ. As we near the peak load, what will happen? These micro cracks they widen and they form new one. So there is more non-linearity that is there in the concrete because of the growth in the micro cracks that are there in the concrete. Okay, stress distribution continuously occurs around the concrete, and if load is removed, there is a hysteresis effect. So you see here, when load is removed, there is a hysteresis effect. There is a permanent strain that is there in the system. And post peak, if we go post peak, what will happen? Micro crack they combine to form a larger crack, which causes softening of concrete. So after this, we see a pattern like this. The stress strain profile will drop. Okay, this is because the micro cracks they have connected and now they are weakening the concrete. They are softening the concrete. Concrete loses its load carrying capacity and becomes brittle. And now, if we will remove the load, there will be permanent deformation. Okay, because of the loss in stiffness. So only up till this before PU point, if we are applying the load, we can achieve some strain recovery. Beyond PU, if we will go, we won't observe any strain recovery because the concrete is now there is major cracking that is there in concrete and it has lost its strength. Okay. Now, how modulus of elasticity is calculated? So basically in lab, we use uniaxial tension or compression loading to calculate modulus of elasticity. Okay, so what this test involves, there are two ways in which we can estimate. There is static modulus of elasticity and there is dynamic. So generally for laboratory applications, we use set static modulus of elasticity. So in this, what we do, in this region up till 30 to 90% of ultimate load, we subject our concrete to cyclic loading. Okay. uh, okay, and then we calculate the modulus of elasticity based on chord modulus. Okay, so you see there are ASTM standard that are present for the static MOE testing, and then this load is applied in the range of pu by 3 to pu by 9. Okay, not here, oh sorry, this is not here, pu by 3 to pu by 9, only at a very small stress level we apply the load. Okay, so that there is no permanent strain in the concrete. Okay, and we keep a very constant loading rate. Okay, so this is a LVDT. Okay, this is basically attached on the surface of concrete. So you see in the background there is a concrete cylinder which is kept at the top, and here you see a LVDT is attached on the surface of the cylinder. And now from the top we'll subject a cyclic loading cycles on the cylinder. So you see these cycles are set. Okay, so this is a preload that we set, and then there are different cycles of load, pu by 9 to pu by 3, then again pu by 9, pu by 3, like this four cycles of loading we are subjecting at a constant rate for a constant amount of time. And this is the profile. Okay, so you see this is the preload, then pu by 9, load is applied, then this is pu by 3, pu by 9, pu by 3, like this cyclic loading is applied on that cylinder, and we get this stress versus strain response. So this you see green line, violet line, and red line. So this green line and violet line are corresponding to two LVDTs. Okay, okay, one is attached on this side and the other one is attached on the opposite side. So why these two are attached? So that we can ensure that the loading is properly applied across the cylinder and it is not just there is no eccentricity in loading. Okay, so if this gap is very small, if the standard deviation is less than 20%, we say that this testing setup is proper and whatever value we are determined is okay. So you can see from here also the deviation in the red profile, violet profile, and green profile, it is within 10%. Okay, it is actually within 5%. So this means that the loading was proper, there was no eccentricity, and then from the slope of this curve, we determine the MOE value. Okay, so this is how this MOE value is determined using static MOE in laboratory. Any doubts in this part?
Yes.
Okay, so let's move ahead then. Now the next is the tensile strength of concrete. So we know concrete is brittle in nature, it is strong in compression but weak in tension. But still tensile strength of concrete is important. Why? Because it governs the crack formation and propagation, it affects the structural behavior under flexure and shear, and it determines the bond strength with the reinforcement. Okay, so we saw when we talked about compression test of concrete, eventually it is the tensile failure that is occurring from the sides. Okay, and when we talk about a reinforced concrete design, then also that tensile strength of concrete usually we neglect, but it is important because initial cracking is happening in the concrete only. Okay, and the bond strength with reinforcement, when the reinforcement is pulling out of concrete, then also there are tensile stresses that are generated inside the concrete. So we see when we increase the grade of concrete, the bond strength of reinforced concrete also increases because of higher tensile capacity of concrete. Okay. So the direct tensile strength of concrete, usually it is only 8 to 15% of compressive strength, and it is generally represented by this equation. So Ft is zero point 0.7 times under root of Fc. Okay, so this is tensile strength and this is compression test, compressive strength. However, since concrete is brittle, so it is very difficult to do direct tensile testing. So suppose this is my cylinder, I can't just directly do a compression, this tensile test on concrete, because it is brittle in nature. So that's why we use several indirect methods to determine tensile strength of concrete, and the methods that we use are split tensile testing and flexure tensile testing. Okay, so in split tensile testing, what we do, we have a cylindrical specimen of 150 diameter and 300 length, and to this, on the curved cross section, we subject it to compression load. Okay. So when the compressive stresses are applied, we know this will generate tensile. It will try to move this. It will apply external axial forces on the cylinder, and since this contact area is very less this time compared to cube, this contact area is very less, so that end plating defect will be very less. So this entire length or diameter of cylinder will be subjected to tensile loading, and we will see a failure in which the concrete will crack from the middle. So this compressive force creates tensile stresses along the vertical diameter, leading to splitting fracture of floating failure of concrete. And using this formula, then we determine the tensile strength of concrete, 2 times the ultimate load at which the cracking occurred upon pi dl. Okay, and then we have flexure testing, in which we have a beam, prismatic beam of 100 cross 100 cross 500 or 150 cross 150 cross 70 and it is placed in 3 point loading or 4 point loading. So if you draw a bending moment diagram of this 4 point loading setup, what you will observe, there will be a part in between which will be subjected to constant bending moment, okay, due to constant loading that is acting from the top. Okay, and this part which is under pure tension, it is then used to estimate the tensile stress of the bottom fiber and the failure when the tensile strength is exceeded. Okay, so for both of these there are different formulas that has been derived. For 3 point loading, we use 3pl upon 2bd square. So this l is the length of the beam, B and D are the cross sectional dimension of the beam, And for four point loading we have PL upon BD square. Okay, and why these formula are different? Because of the difference in the bending moment profile in both the things. So generally in this, the failure happens at the weakest link where the bending moment is maximum, that is in the middle part. Okay, so from the middle the failure will happen, and that will be due to flexure failure, and that is used to determine the tensile strength of concrete, because direct tension determination is difficult. Now try to answer these two questions based on flexure and tensile strength. And if you have any doubt in this part or tensile stressing, you can ask now. How much you will work? Until my class will be there, you will work.
It's actually at 40s. I can shut up.
I have 20 more slides.
You can see the graph.
I'm tired.
So it will go till 8:30.
It will go long today. Okay, let's see the answer. So the first question, a high performance concrete mix was tested for flexure strength and split tensile strength, and the value recorded are shown to you. 7 MPa for flexure and split tensile we got 4 MPa. And what you can infer from this? Why flexure strength is more than split tensile strength? Can anyone tell me? The option that you chose is correct, but why? Why it is so? Okay, so it is due to the way the loading is applied and the way stress is distributed in the system. So if you see in flexure test, the specimen is experiencing tension at the bottom and compression at the top. So the failure is governed by the tensile cracking that is happening at the bottom. However, in split tensile strength, the stress is uniformly distributed across the entire diameter of the specimen. Okay, and it has a more direct measure of tensile strength. Okay, in this there was only bottom fiber which is under tension, not the top part. So that's why you see split tensile strength is lower compared to flexural strength, because in this the entire cross section was uniformly subjected to tension rather than only just the bottom part under tension. So in this beam, what will happen? Above this neutral axis, it will be under compression, lower will be in tension. But here, the entire cross section is in tension. Okay, that's why the split tensile strength is lower, and we say flexural strength is always higher due to stress distribution. Question number 16, 17. Two concrete cylinders of same mixture design were tested, but of different shape. So this cylinder has a larger size and this has a lower size. So if for cylinder A I'm getting a tensile strength of 3.8 MPa, what will be the tensile strength of cylinder B? It will be more than that, less than that, or similar. Okay, so yes, the correct answer is B, more than that due to lower size. So as we saw in compression, higher the size, more will be the probability of flaws or micro cracks that are present in the concrete, and that will lower the strength of concrete. Okay, so that's why a smaller size specimen will give, which may give me more than 3.8 MPa of tensile strength. Okay, and for this, the correct answer was A. Okay, now let's come to the next part, which is multi-axial loading. So if you see right now, whatever we have discussed, it is about uniaxial compression. However, in reality, there can be multi-axial and triaxial compression also, which can act. Okay, and a classic example of this biaxial and triaxial compression is the FRP wrapping that we do on concrete. So this is just a part that we do for retrofitting. So when we design a concrete, suppose on field we want a M60 grade concrete, but due to flaws in mixture design, it was made M40. Now, whatever structural design was done was before M60. It was not for M40. So we need to strengthen the concrete. And for that, one of the ways is FRP confinement. So what we do around concrete, we use a FRP wrapping. So FRP is fiber reinforced polymer. So they are wrapped around the concrete and they create a confining effect. And this confining effect is similar to biaxial compression or triaxial compression. So what is this confining effect doing? Okay, so earlier we have seen that tensile stresses are generated near the middle, which causes a concrete cylinder to fail. Now FRP provides the compressive stresses, the confining stresses to the cylinder. So this will resist the tensile stresses and it will make concrete stronger in compression when the axial load is applied on it. Okay, so this is the concept of biaxial and triaxial compression. So if you see here in this curve also, under biaxial loading, the strength was this. However, if there is under uniaxial loading, the strength was this. But any amount of biaxial loading, it will increase the strength. Okay. So if I have some compressive stresses acting from the sides, it will increase the strength of concrete under axial loading also. And the same it's seen here. Okay, this is the confining stresses. So as the confining stresses are increasing, the axial stress of the concrete is also increasing because of the confining effect that those forces are creating. However, if this force is tensile in nature, then what it will do, it will weaken the concrete rather than strengthening the concrete, because already these tensile stresses that is generated due to the loading, and now these stresses are also there, so it will weaken the concrete. So the direction in which the confinement is applied also becomes important. Okay, now let's see the long-term behavior of concrete, which includes both creep and shrinkage. So what does creep means? So creep is simply long-term deformation of hardened concrete. So suppose you have a concrete structure which is subjected to compression, not for the peak load, but for a lower than peak load, but for a longer time. Okay, so in this sustained loading, what will happen? There will be increase in strain without change in the applied stress, and this increase in strain is known as creep. Okay, and this creep occurs due to slow continuous movement within the material, which leads to progressive change in the shape over time. So you can see one example of this creep acting in this image here, where you can see a bridge deck under continuous loading. It starts to show vertical deflection, or we can see creep deflection, where you can see here, this is the beam, and over time, due to sustained loading, this has deformed, that has deflected from the middle, and that is due to creep. So in this diagram, the same thing you can understand from this diagram also. So you see here, in this image, in this diagram, we have a constantly applied stress that is acting on a system, and under this constant application of stress sigma naught, after an initial elastic strain that is generated due to the modulus of elasticity of material, over time, if we keep the stress constant, they will see there is more strain that is generating in the concrete due to creep. Okay, so this creep after time t naught till time t, it is due to the strain that is increased is due to creep. Okay, and this phenomena affects the structural stability by altering the dimension and the internal stress distribution. So generally, deformation due to creep is divided into three stages. So initially, if you see, when the load is applied, there is instantaneous strain that is due to the modulus of elasticity. Initially, the primary creep will be there, which is slow and with time, and it starts rapidly and it slows down. Then there is secondary creep, where it is almost constant; it is increasing at a uniform rate. Okay, here we can have cyclic loading cycles also, which is there. And then there is ternary creep, where there is accelerated deformation before material failure. So this pattern that you are observing from stage, this initial stage to final stage, it can have three cycles in between. Initially the creep rate will be in strong, then it will become linear, and then it will take a sudden growth as the cracks will form, cracks will grow, and cracks will connect and propagate uncontrollably. And what happens when we remove the loading? There will be a process which is known as relaxation, or we call it as creep recovery. So you see here and again in the diagram, after elastic strain, there is creep strain until the loading. Now the concrete is unloaded, so the elastic part will show some recovery that we saw from the hysteresis. Okay, we talked if we are not applying the load up till ultimate load, then there can be a slight recovery in the strain. So that is this hysteresis effect in the elastic recovery. Some part of the creep will also recover, okay, based on the amount of cracking that has occurred. However, there will be a big irreversible creep part that will be there in the system due to the cracking that the concrete system has suffered until this loading period. Okay, so this is a representation of creep recovery or creep relaxation. So if you see here in the text also, same thing is mentioned. When continuous load is removed, the strain decreases immediately. The amount of decreased strain is equal to elastic strain at the given age. Okay, this quick recovery is followed by a continuous decrease in strain, which is known as the creep recovery. This is the part of the creep recovery, and that is a part of total creep strain suffered by the concrete. So this total strain, out of this, a small portion is recovered and the remaining portion is irreversible. Okay, now there are different factors that can affect creep. Influence of aggregate. Okay, aggregate, they undergo very little creep. Okay, so they are responsible, it is really the paste which is responsible for creep. So if we have stronger aggregate, we have less magnitude of creep, and if we increase the aggregate proportion from 65 to 75%, the creep can decrease by 10%. That has been found in literature. Influence of paste: if we have more amount of paste, it is there is chances that they can undergo higher creep. So creep increases if we increase the W by C ratio. And influence of age: as the concrete hardens, what will happen? There will be less moisture that will be there in the system. This paste will harden, so creep will decrease. So generally, creep versus age, if I plot for a certain concrete mixture, it will be linearly decreasing. Then influence of volume to surface area. So if we have a higher surface area, we'll have a lower volume to surface area ratio, and there we have more creep because more surface is exposed to environment where more moisture loss can occur and higher creep deformation can occur. Okay, however, if this volume to surface area ratio is higher, there will be less creep, and that's why in dams and thick walls, mostly the moisture remains trapped inside and there is less creep effect in concrete. And the similar thing is shown in this data scale also, where you see as the volume to surface area ratio is increasing, the creep effect is decreasing because there's lower surface area which is exposed to environment. Okay, now try to answer these three questions based on creep. So these are very direct question, you will easily able to answer. So just try to be quick for this part so that we can finish the session on time and we can have a little post session discussion also. Just try to answer these questions quickly, like within 2 minutes. Okay, so yes, for question number 18, the answer is B. Okay, so primary reason why high strength concrete exhibits lower creep than normal strength concrete, it is due to the dense microstructure. So we have a stronger cement paste matrix in high strength concrete, which is subjected to less creep, and lower porosity. Again, since there is lower porosity, there is lower moisture loss from concrete, and there is weaker crack propagation over a sustained loading inside concrete, which contributes to lower creep. For question number 19, I am getting answer as D. Okay, which environmental condition will accelerate creep in concrete the most? Okay, so more is the drying effect, or more is the exposure to a certain condition where along with sustained loading there can be moisture loss, there can be cracking inside the concrete, the more will be the creep. So that's why we have high temperature and low humidity as the most critical condition to accelerate creep. So what happens? High temperature, it accelerates the moisture movement, or lower humidity increases the drying, and both of these contributes to generating more cracking inside concrete. So this is more related to a shrinkage. More will be the shrinkage, more will be the cracking inside concrete, and then more will be the creep effect in concrete. Okay, so submerged condition in water, it won't uh, give more rise to shrinkage issues in concrete as compared to this high temperature and low humidity condition. Okay, so that's why the correct answer will be A. Which factor has the most significant influence on long-term creep behavior in concrete? So the correct answer will be A again. So higher is the W by C ratio, more is the porosity, and then higher will be the risk of creep effect due to moisture movement and weak cement paste structure that is there inside the concrete. So that we have all understood from these points that we discussed. Okay. Any doubts in these questions? Okay, so let's move ahead. So after creep, the final part in the hardened properties of concrete is the shrinkage in concrete. So how we define shrinkage? So shrinkage is basically defined as the volume changes that is occurred in concrete due to loss of moisture at different stages due to different reasons. So there are basically four types of shrinkage: plastic shrinkage, drying shrinkage, autogenous shrinkage, and carbonation shrinkage. So plastic shrinkage is contraction in volume due to water movement while concrete is still in plastic state. So that is the time before concrete hardens. During that time, if there is some water movement or moisture loss inside the concrete, then it contributes to plastic shrinkage, and this mainly occurs due to loss of water by evaporation from the surface of concrete. Okay, it can also occur due to absorption by aggregate if it is not considered during mixture proportioning. So that's why when we do mixture proportioning, we take moisture correction effect in aggregate. Okay, and if it is not taken, then plastic shrinkage issues can rise. Okay. Second type is the drying shrinkage, which is caused by loss of surface absorbed water by this calcium silica hydrate. Okay, this is drying shrinkage, and it takes place once the concrete has set. Okay, so before setting, the shrinkage that is happening, it is known as plastic shrinkage, and after setting, the shrinkage that is happening, it is known as drying shrinkage. And how drying shrinkage occurs? When we are subjecting concrete to hot and humid condition. Okay, so under such condition, over time, water held by gel pores in calcium silicate hydrate structure, they can also evaporate, and that is known as drying shrinkage. Okay, this type of shrinkage can be recovered also if we again try to immerse the concrete in water. Okay, however, it won't recover completely, but there can be slight recovery that is possible. Then autogeneous shrinkage, it is known as basic shrinkage also, and that is something that will occur. We can't stop it. It is due to the chemical reaction between cement and water. Okay, so when cement and water reacts, there is a slight reduction in the volume. So the volume of cement and water individual components, it is more than the volume of cement paste that is formed. Okay, and this is what is known as autogeneous shrinkage. So it does not include any environmental effect that, such as temperature and moisture, and its magnitude is usually ignored when the W by C ratio is more than 0.4. So this type of shrinkage, it is present in a very small amount, but it is bound to occur. Okay, and final type is carbonation shrinkage. So when CO2 it reacts with calcium hydroxide, it forms CaCO3. Okay, that we saw in the lime cycle discussion also. Okay, slake lime upon reaction with CO2 it forms calcium carbonate, and this new product has a lower volume compared to the reactant, which can lead to shrinkage. So such type of shrinkage is known as carbonation shrinkage, and these two shrinkage, autogeneous shrinkage and carbonation shrinkage, they are much smaller compared to plastic shrinkage and drying shrinkage. So the main shrinkage problem in concrete is either during before setting due to plastic shrinkage, or after setting due to drying shrinkage. So that's why before setting we keep concrete covered properly under inside molds so that we can avoid plastic shrinkage, and after setting we keep concrete in curing condition so that there is no loss of moisture from inside, which can cause any shrinkage issue or any delay in the hydration process, or a problem in the hydration, to avoid this drying shrinkage. Okay. Now different factors can affect shrinkage in concrete aggregate content. So these will be similar to what we talked in creep. Higher is the aggregate proportion, it reduces the shrinkage because it gives stiffness to the concrete. If WIC ratio is higher, more will be the shrinkage. If curing is not done properly, there are chances of water evaporation, then shrinkage will rise. If there is low humidity, there will be more moisture evaporation, more will be the shrinkage. If higher is the surface area of concrete, there is more surface available for moisture loss, so more will be the shrinkage. Higher is the slump, means there is more water in the system, so more will be the shrinkage. Fine aggregate, higher is the fine aggregate proportion, more will be the more will be the paste content in my concrete, so more can be the shrinkage. If there is more air content, then it will reduce the shrinkage, but because it will provide that relief inside the concrete, which can reduce the shrinkage. And higher the cement content, more with the heat of hydration, more will be the cement paste, so more will be the shrinkage. So every factor, it is related to the movement of moisture, or which more will be the paste or more will be the moisture inside concrete, more will be the shrinkage issue inside concrete. Okay, so this I have not discussed in detail because it is already similar to what we discussed in creep. Okay, so that's why I moved quickly in this. And in this image, you can see different ways in which shrinkage cracks are generated. So you can see here, this is a typical building plan. Okay, and there are different types of cracking that are present in this image. The A, B, C are the due to settlement. However, this D, E, and F. So you can see here, here, and here. These longitudinal and transverse cracking, they are due to shrinkages, and you can see they are all at the slab surface where there is a higher surface area that is exposed to the environment. So like such cracks can appear due to shrinkage in a structure, if it is not cured properly, or if it is not taken care properly during the initial strength gain phase. Okay, just try to answer these two questions quickly now. What you wrote no for, can you just tell me which thing, which question is a problem?
No, no, sir. You ask any doubts. That's what I told.
Okay.
No, sir.
Just try to answer these two questions properly, and then we'll move to the final segment of this class. It will hardly take 5-10 minutes to complete that part. Okay, so yes, for 21, the correct answer is B. Okay. Which of the following condition will result in highest drying shrinkage? Higher W by C ratio or higher fine aggregate content. So this increases the cement paste volume inside the concrete, and more is the moisture, more is the paste contents inside the concrete, there will be more chances of moisture evaporation, and thus there will be more chances of shrinkage. And higher W by C ratio also reduces the strength of concrete, so that can also affect the increase chances of cracking due to shrinkage. For 22, which of the following statement is false regarding shrinkage induced cracking? Can anyone tell me the answer for 22? So we saw these different reasons. Okay. So there is one clear cut answer in this question. Just try to think why shrinkage is occurring. No, D is not the correct answer. Shrinkage cracking can be reduced using internal curing techniques. So, if we are improving the curing of concrete, then shrinkage cracking will be reduced. This is a right option, but I am asking which of the following statement is false. Okay, so out of these four, three are right. One is wrong. Which one is wrong? Internal curing, if we are doing, we are reducing the shrinkage. That is true because we are reducing the moisture loss that can happen. B is also not right. B is also right, but it is not false. Restraint from reinforcement can lead to uh, shrinkage induced cracking. This is also true. There is something known as top bar effect. Okay, so what happens when there is reinforcement inside the concrete? When we pour a very flowable concrete, what will happen below the reinforcement? There will be a kind of air gap that will be created, and that can be a source where cracking can happen inside the concrete. Okay, so they can also lead to shrinkage induced tensile stresses inside concrete. So this is a little advanced concept that I will try to cover later on. This is known as top bar effect. Okay, if someone wants to refer. So the correct answer will be A. If you see, it was clearly mentioned here. Okay, shrinkage cracks are more likely in members having high volume to surface area ratio. This is not true. Why? Because higher the volume to surface area ratio means lower is the surface area. If there is low surface area, then there will be low chances of shrinkage cracks because there is less exposure to environment. Okay, so shrinkage cracks are more when there is low volume to surface area rather than high volume to surface area. Just focus on the surface area part. Surface area is important for both creep and shrinkages. Okay. Now let's move to the final part, that is the reinforcement material. So this part is relatively easy because reinforcement is an industrial product. We have more control over reinforcement. So when we talk about reinforcement that we use in reinforced concrete, they are of different size. From 8 mm to 32 mm reinforcement can be used. Which diameter to use? It depends upon the type of the component and the direction of placement of rebar and the design. So if you have seen the design of reinforced concrete as per IS 456, if anyone has done, you will find the area of steel reinforcement that we estimate, it can vary based on the diameter of reinforcement, and then the choice can vary depending upon the spacing between the reinforcement also. So both spacing and the amount of area of steel that we require both determine which reinforcement sides we can use. And direction of placement, generally longitudinal bars that we use are from 12 to 32 diameter. 32 is rarely used, it is maximum up till 25 that we use. And the transverse reinforcement, the stirrups that we make, it is usually 8 to 12 diameter in size. Okay, so based on the application, there can be different sizes. Now, this reinforcement material is mainly of two types. There is mild steel bar, which is plain and round, and there are deformed steel bars, which are ribbed. So these mild steel are mainly used in construction and expansion joints. But for when we talk about reinforced concrete, we are using ribbed reinforcement. So these are the ribs. Okay, on the top, so you see, mild steel has a plain surface, whereas ribbed reinforcement has some groovings on the surface. So what this grooving does, it reduces the slippage and improves the bonding. So when we talk about reinforced concrete, this is my reinforcement and this is my concrete cover. Due to this presence of ribs on the rebar, it provides a mechanical interlock with the concrete cover, which increases the bond strength of reinforced concrete. So that's why when we talk about reinforced concrete, we use a ribbed reinforcement. Now, the steel can also be of different types. This reinforcement can also be of different type. There is thermomechanically treated reinforcement, high yield strength deformed reinforcement, and cold twisted bar. All these types differ mainly in terms of grade. Okay, grade can be a difference, and the way in which they are manufactured. Okay, so I will explain you one of these types, that is thermomechanically treated reinforcement. So in this, what we do, we heat the reinforced steel up till a very high temperature, and then we do a sudden cooling. Okay, so what this does, it creates a outer coat of martensite. Okay, martensite is one of the composition of steel that is present at the outside, and inside will be a ferrite perlite microstructure. So this martensite is strong and brittle, and from inside it is soft and ductile. So it provides a dual nature to a reinforcement bar. So in this way, there can be different ways in which a reinforcement can be manufactured. Now, there can be different grades. So if you see, like concrete, we have M20, M40, M60. Here also we have different grade designation: Fe415, Fe500, and Fe250. So this Fe represents iron and 250 represents the yield strength. Okay, so here you can see this is the yield strength of my steel. The modulus of elasticity will be the same for all the three cases, because the composition of steel is the same. Just the strength of the steel is changing, which is based on the manufacturing process. However, just like concrete, if you see, the ductility of steel decreases as the grade of steel increases, just like what we saw in concrete also. Okay, so this strain corresponding to ultimate load, it is increasing as the grade of steel is increasing. However, the ultimate strain before failure is decreasing as the grade of steel is increasing. So this is more ductile and this is more brittle material. Okay. Now, for concrete, we saw there are two factors that were applied in the design. However, for steel, there is only one factor that is applied from characteristic curve to design curve. Why? Because it is an industrial product. There is more control over its manufacturing rather than in concrete. So in steel, we know the yield strength and we apply a factor of safety gamma s, which is taken as 1.15. For concrete, it was taken as 1.5. Here we are taking as 1.15. Why? Because it is an industrial product. There is less variation in its property compared to what variations can be observed. We can observe in concrete. So you can see this 1 divided by 1.15 will give you a factor of 0.87, and this is what we use for design. Okay, so when you talk about this again, if we go to this stress strain diagram for a reinforced concrete element, we saw this compression block earlier, and for tensile block, you see we use 0.87 Fy for designing. So factored load for steel also we take for design like this. Okay, and the strain corresponding to this factored load is taken as 0.87 Fy upon Es plus 1.002. So this is the strain corresponding to this load that is taken for design. Okay. Now, generally, when we talk about reinforced concrete, it is a compatible material. So we assume that it can have a very high lifespan. However, in reality, this is not true. Why? Because this material reinforcement is in a higher energy state. It will try to convert into its original form, and due to aggressive ions that are present in the atmosphere, and these ions can lead to corrosion of reinforcement steel. So corrosion is a very big issue when we talk about reinforced concrete. Over time, when we'll talk about durability, we'll understand more about this corrosion. Okay, so generally this normal thermomechanically treated reinforcement or plain reinforcement, they are not good enough when we talk about severe exposure conditions like in Mumbai or any area which is near the coastline. So for them, we have special reinforcements also that we use in design. There is stainless steel, which has high chromium content and strong a protective layer. There's fusion bonded epoxy coated rebar, cement polymer composite rebar. So these are coated rebar. So over rebar, there is some coating which are present in both of these cases, which provide more resistance to aggressive environment, and it these are also used as a reinforcement material. However, nowadays there are fiber reinforced polymer also which are used as an alternative to steel reinforcement. So what is happening here? We are completely eliminating steel from the picture. So we are completely eliminating the corrosion issue, okay, from reinforced concrete. So there are glass fiber reinforced polymer, there is carbon fiber reinforced polymer rebar which are present in market, which are now started to be used in reinforced concrete. But there is one problem with this. Though they can't corrode, but they are not as ductile as steel. They are brittle in nature. So that's why they can have higher tensile strength or modulus of elasticity, but they can show brittle failure. And why we are using reinforcement in concrete? To provide to provide ductility to concrete. Okay, and that ductility won't be achieved if we are using FRP bars. Okay, so that is one of the issue with FRP, and also they are costlier compared to normal reinforcement bars. So though this technique is growing, it has still some issues or still some controversies to normal steel reinforcements. Okay, now just try to answer these final three questions for the session. Okay, very simple question regarding reinforcement material. In the meantime, if you have any doubt regarding any of the discussion that we had today or any assignment question which you have submitted, that you can discuss. Okay, so for 23rd question, which of the following rebar is more suitable for marine structure exposed to high chloride concentration? So for those who don't have background to this chloride thing, so chlorides are very critical source of corrosion in steel reinforcement. Okay, so if they are critical source, we need some type of steel which can resist chloride attack in a better way. So we can have galvanized steel bars. Okay, galvanization is done to improve the resistance against external attack. Or we can use glass fiber reinforced polymer bar also, which don't have steel in their composition, so their corrosion won't be an issue. Okay, though it is brittle, it can be an option. Which of the following is a limitation of CFRP bars as reinforcement? So this we have just discussed right now. The answer is clear. Okay, yes, the answer is C. Okay, brittle
See,
failure. Okay, because CFRP, it shows brittle, it is more brittle, it is not as ductile as steel reinforcement. So you would have seen one curve in the session discussion. I forgot to attach that slide here. So there you can see these are brittle material. They don't have that much. They can have that much strength, but they fail at a very early age. Okay, their strain at failure is low compared to what we observe in steel. So in steel we have a certain elongation that happens, then there is neck formation, and then there is rupture that is happening in the rebar. However, in this CFRP and GFRP bar, there is brittle failure. They don't show any elongation or necking before failure. Which of the following statement best describes epoxy coated rebar? So what is this epoxy coating doing? Can anyone tell me? No, it is not a cathodic protection. Cathodic protection is done by this galvanized steel bar. Okay. So epoxy is not reacting with anything. Epoxy is just there at the surface. When we do galvanization, we are adding a zinc coating over the steel. And that zinc is reacting and sacrificing itself instead of steel reacting. So that is known as sacrificial activity. Okay. So this is not the correct option. Any other guess?
see,
Yes, the correct answer is C. Okay, this epoxy layer, what it is doing, it is forming a physical barrier. It is an insulator coating. It doesn't react with the environment. It will just create a physical barrier between steel and external environment, and it will stop the interaction between two, and it will delay the corrosion. It is not perfectly insulated because it also has pores through which ions can propagate, but still around 3 to 4 times more life epoxy coated bars can give compared to normal TMT bar if it is not uh, damaged. Okay. Okay, so this was all about today's session. Okay, we discussed about cement, then we discussed about strength, then creep and shrinkages, and finally we talked about reinforcement material. Okay.